Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Jamie Rankin with us today. Hey, Jamie.
Hello, thanks for the invitation.
Well, thanks for agreeing to talk about your very awesome APJ letter. Very cool. And Jamie, where are you located at? What's your geolocation?
I'm in Princeton, New Jersey right now.
Okay. Is it spring? Is it summer?
It
It's
it
snowing.
actually can't quite decide. It's transitioning from a lot of rain to kind of a nice, pleasant spring, but gets hot with summer-like conditions too.
Okay, very good. So it is April 19th of 2023 as we record this, and I'm in Phoenix, and we are definitely sliding into our warmer weather, let's put it that way. Very good. Very good. And Jamie, what do you like to do for research?
For research, I actually like to look at the extreme locations of kind of spacecraft measurements. So, for
Cool.
example, I measure cosmic rays, and I like to see where they are kind of coming in as they're coming into our heliosphere. And
Okay.
I like to see as they get really close to the sun. So I actually work on Parker Solar Probe, which is the
Cool.
closest spacecraft human-made object that's ever been, put towards the sun. And then I also work on Voyager, which is the furthest man-made object from the sun. And
Both of
exactly, and I like to trace how cosmic rays come in from all through both locations and all directions. But I also just love looking at interstellar space. Interstellar space is my first love because I started looking at interstellar space as a graduate student of Ed Stone.
them.
And I started my graduate career 5 days after Voyager 1 reached the interstellar medium, after it crossed the helipause, went into the
Okay.
interstellar medium.
Cool.
So it
Very
was a fun time there to see history being made. Um, and I just got a random phone call. Anyway,
cool.
and so during that past, I guess now decade, which is hard to believe, we've had 10 years, 11 years of measurements in the interstellar medium, and it's incredible. And the
Cool.
cool part about the interstellar medium, which is my favorite part about it, is that a lot of stuff we see there can't ever make it inside our heliosphere, and it can't ever be detected at Earth. It can't be ever detected by anything else right
Yep.
now. So it's pretty
It's awesome.
exciting.
Very cool. Very exciting. And that is going to bring us to this most awesome APJ letter. It is open access, people. It's the open access era. You can go grab a copy for free. Go get one. Unified picture of the local interstellar magnetic field from Voyager and IBEX. And Jamie, take us away.
All right. So one of the surprises with Voyager's reaching the interstellar medium is basically how the magnetic field has behaved. Because when the Voyagers crossed the helipause, which is basically the plasma material boundary that separates us from all of our solar wind and its materials, and then the interstellar medium and its materials, when we cross this helipause region, there's an abrupt change in cosmic rays, but there's not hardly change in magnetic field behavior direction. And people were a little surprised by that. And then a couple months later, there were these radio emissions that occurred. Just the sun, kind of some sun transient produced transient, basically had pushed and made this little wave that reached out into the interstellar medium, and it was detected in the radio frequency range, but that gave a hint of what the plasma density was out there, and that pointed to being the interstellar medium. And because Voyager 1 didn't have a working plasma instrument on board, this fortuitous plasma event that just caused a little ringing sound in space that the radio instrument picked up. It was a beautiful way to tell that we had arrived in totally different plasma than we'd ever been before, which is this very local interstellar medium. And the big picture, could you actually go up real quick to the introduction?
Sure, absolutely.
No worries. So the big picture is that the Voyagers are out here, and they're taking their journey, just a line of sight journeys through the heliosphere at their different trajectories. Voyager 1 is about 35 degrees north of our ecliptic plane, where all the planets are. And then Voyager 2 is about 35 degrees south of the ecliptic plane. So they
Okay.
kind of go in different sort of angles, and they take their measurements just locally. All the materials they encounter are just being directly measured in spot, kind of like a road trip. If your car is traveling on a distinct highway, you
There
know,
you
you can see what scenery is around you, but it doesn't necessarily give the big picture of what that environment is.
Yeah.
So there's this other mission called IBEX that launched around just before the Voyagers arrived in the interstellar medium.
Mhm.
And this mission actually has a clever way of remotely imaging the whole kind of boundary of the heliosphere and the termination shock, and basically seeing a 360-degree view of what is the map like. And that'd be more like an aerial drone view.
Cool. Oh, yeah.
By taking advantage of these particles that are neutral from the interstellar medium, and then as they enter into our heliosphere, they become ionized by the solar wind, UV radiation.
I'm with you.
They come back outward, and then they might become neutralized again, and they can be detected by this special spacecraft, this much smaller mission than the Voyagers, IBEX, that is basically located in Earth kind of distance from the sun. And so this can remotely image what is happening, all these processes that create these special neutral atoms, is basically a way to remotely detect what the plasma is like in the boundaries of our heliosphere. And so in this paper, it was very interesting opportunity to bring both of these perspectives together. We have this 360-degree sky map, but it can't tell distances very well or anything. It's just all integrated over the line of sight. Yes. And then you have the Voyager kind of single points along the way trajectories. So we're combining them in this paper. And one of the neat results that IBEX mission has returned, and this is back in 2009 or so, one of the first results was the existence of a certain band of enhanced neutral atom fluxes in the sky called the IBEX ribbon.
Okay.
And the location of this IBEX ribbon allowed the team to determine what the pristine local interstellar magnetic field looks like. Awesome. So the magnetic field far beyond the sun.
Yeah.
And before it gets draped around our heliopause, because our heliosphere is kind of like an obstacle. It's like a boulder in a stream, and the water flows around it and diverts around it. And so it's currently thought that the magnetic field, the reason that the Voyagers didn't see a change in magnetic field is simply because all those interstellar magnetic fields are just kind of draping around our heliosphere. And it's two magnetized plasmas. So the heliosphere has this solar magnetic field and that plasma. And then our interstellar medium has a totally different plasma environment, and they can't intermix. And so they kind of divert around. This flow of the interstellar medium diverts around. And so what this paper does is it combines the Voyager and IBEX observations to try to understand what this tells us about the very big picture. How does the field wrap around our heliosphere, and then how does it undrape, and how far away will it kind of undrape to the magnetic field that the pristine interstellar medium sees? And so that is the big picture of what this is looking at.
Cool. Very cool.
Can we go down to figure 4?
Figure 4. Let's go down to figure 4. Oh, and there's a lovely global perspective. Okay.
So this left-hand side is what we'll focus on. And those lines there kind of indicate how the interstellar magnetic field, that's what ISMF means, how they kind of approach our heliopause, HP, and our heliosphere, and how they kind of get perturbed by that obstacle of the heliopause. So they kind of bend around like that. And these results were determined from the IBEX mission. And so now, basically, we're taking the line of sight kind of measurements from this model that was fitted to a bunch of IBEX data, self-consistent model that has the full sky picture, but they can also kind of predict what the Voyager magnetic field should be from the time it crossed into the interstellar medium, and then how does it unfold. And so we directly compared that with the Voyager. Each Voyager basically set of observations of magnetic field in the spacecraft coordinates frame, just a direct comparison to what Voyagers directly report.
Right.
That is in figure 1.
Figure 1, I'm with you here. And 1 second there. Figure 1, let's slide up and take a look at that one if I didn't go too far. Figure 1.
Okay.
I'm with you. Yes. Yes.
There we go. And so the way that the Voyager spacecraft coordinates work is there's this radial component, that's the top panel, B of R, and that's just looking from the spacecraft back towards the sun. And then there's tangential and normal coordinates, and those are basically perpendicular, and they complete that sort of triad. And it turns out that there's a really nice agreement between this N component and the T component. And then there's like somewhat of a disagreement in this radial component. But we're surprised because the model is completely independent of any sort of assumptions from Voyager. And so the amount of agreement that this shows is pretty encouraging here.
Indeed.
And so basically we had to naturally kind of wonder about what's happening with this one R component to explain this, but basically for the most part these N and T components agree really well, and the magnitude of the magnetic field, which is just the sum of the square of each of those, B squared plus T squared plus N squared, and take the square root. That also is kind of slightly off a little bit, but it's not terrible either. And a fun little thing to talk about too, just briefly, and I'll get back to this very end, is you see that at a radial distance of 150 astronomical units, there's this really strange thing that happens where the magnetic field just suddenly changes. And we don't know what that is. That is totally unknown, unseen before, and we're trying to understand that. It's a hot topic. But as you can see, these blue lines here, with each blue line, there is a change in how the magnetic field behaves.
Got it.
That is known to be caused by these events from the sun that can basically merge as they journey, and they can make their way all the way out to the heliopause, and they can push waves and cause shocks in the interstellar medium. So the sun makes waves in interstellar space. That's the detection of those things. And this model is a static time invariant model. So the model in green doesn't account for any of those perturbations. So we're just highlighting that is an important difference between the model and the simulations in how the physics really is in nature.
And just to orientate, the red line here is the Voyager 1 heliopause?
That is correct.
Right, I'm with you. That shows I'm with you. Okay, very good, I'm with you.
All right, so this is Voyager 1, and as you can also see, Voyager 1 has spent much longer time out there, about 11 years or so. And then Voyager 2 joined its twin in, we should actually move to figure 2, sorry about that. More recently joined its twin in 2018, end of 2018. And that's what this data shows, is just the data we have so far from the short time that Voyager 2 has been in the interstellar medium. And as you can see, there's kind of a similar story where this N and T component is pretty promising. And you do see disturbances and time variations in the magnetic field, which are those blue vertical lines. And then there is a disagreement again in that radial component.
Larger this time.
And so in making these comparisons, we were very encouraged overall with what we found, because the model is just completely independent of Voyager. And we were also very interested in trying to understand more about why this R component doesn't agree. And of course, the models aren't perfect. However, we do point out in this paper that the way that the components of the N and T coordinates get calibrated on the magnetometer, it basically requires the spacecraft to roll around the sun pointing axis. And that roll maneuver that is performed on the spacecraft allows them to subtract out the spacecraft magnetic fields, which are much stronger than the magnetic fields measured in the interstellar medium. And so that has been calibrated, the N and T components have been calibrated the same way throughout the whole history of the mission and by these roll maneuvers, magnetometer roll maneuvers.
Cool.
However, this R component cannot be calibrated the same way. And so we basically say, it's probably worth looking at the R component and what the assumptions are being made, see what, here's an idea of how sensitive we are to that component. And sure, maybe it could be something with the model too, but the odds of it being the same component on the same spacecraft and that being the component that is a lot trickier to calibrate, we just basically encourage the team to have a closer look at that. And it's really hard to find data that you can compare with, in interstellar space. So it's the one-of-a-kind data, but it's nice to have a model that can kind of give hints. So figure 3.
Yeah, I just wanted to comment that BR is also smaller in magnitude than either of the two.
Right, that's true too.
That's true for Voyager 1 as well.
Yes, it is.
A little closer, not quite as big of a difference, but okay. Anyway.
Yeah, no worries. Yeah, so it's just a kind of a hint of, hey, let's take a look at this and try to understand fully. And then the next figure, figure 3, is where we're actually really looking at the sensitivity of this component. So here we basically take the raw Voyager data and directly compare it with the model. Okay. And what those arrows show is just how do the Voyager magnetic fields trend as a function of distance away from the sun. And so it looks like Voyager 1 is kind of trending in that interesting direction towards positive longitudes.
Yes.
Voyager 2 is trending in a different direction.
Mm-hmm.
And that's a puzzle by itself. Even regardless of having a model to compare with, the magnetic fields should eventually point in the same direction as you get further and further away from the heliosphere. Because there's only one magnetic field out there. So they should eventually converge to the same interstellar magnetic field value. Even if you don't know what that value is, they should eventually rotate towards the same direction. But that doesn't appear to be what is happening.
Right.
That's very strange. And then the arrows in pink here show how the magnetic field behaves in the model. And again, this model doesn't have time variations and things like that. Okay. But from the IBEX data, it implies that this data-driven model implies that the fields should kind of unwrap and then point to where that star is, that B at 1000 AU, that's the speed interstellar medium. And the IBEX data robustly gives a value for where that magnetic field direction should be.
Okay.
And so on the right-hand panel,
let me ask one naive question.
Go ahead.
What is a nose?
Oh, that's a great question. Yeah. It turns out that when we're moving with respect, our whole heliosphere is moving with respect to the interstellar medium at speed of 26 kilometers per second. Okay. And the nose is basically that direction that's leading the whole motion.
Okay. It's following your nose. Got it.
It's literally following your nose. Yeah.
Following your nose. Got it. Okay. Yep. Thank you very much. Okay. Yep. And now we're going to substitute from the model. Okay.
So in this figure, basically we keep all of the same other components, T and N, that Voyager sees. And we were just curious, could this kind of discrepancy between the two Voyagers, is that a function of, is it sensitive to R, basically? And so we are by no means suggesting that all the Voyager data should be like replaced with a model or something. No, we just want to see how sensitive are we to this R component. Could it be the reason that these the two Voyager directions disagree in how the magnetic field's unfolding? Okay. And it looks like that putting the R from the model into there does tell a consistent story of how the fields might be starting to point towards the same direction. And so this is all to say that this R component is a very important player and how we understand how this magnetic field behaves when looking at the data and comparing it with models. So at least we've isolated kind of where are the challenges here in telling the story, and then what does this mean for the big picture? So that's the exciting takeaway, which is big four, is if we believe the model, and there's much reasons to believe it, you know, with the caveat that it's not real life in terms of having the perturbations as a function of time, because these shocks, these waves. But for the most part, this gives us an idea of what the Voyager should see in their futures. So the magnetic field there is in the black. That's basically the angle of the magnetic field compared to the interstellar unperturbed magnetic field. So how far away is the current, that magnetic field at say 200 AU is about 30 degrees away from what the unfolded, undraped magnetic field would be.
Yes, I'm with you. Okay.
And so the blue shows the magnetic field strength. So actually on this left-hand plot, you can see how there's a bunch of red coloring around near the helipause.
Yeah.
And that's because the field is more squished in towards the Voyager 2 direction than the Voyager 1 direction. And that means it's a stronger magnetic field there. And that squishing in actually was observed also by Voyager, where the magnetic field is roughly, we deal in nanotesla, it's roughly 0.6 to 0.65 nanotesla at Voyager 2, and it's around 0.4, 0.45 at Voyager 1. So we do actually see the evidence of how it gets squeezed when it's draped around. And then it unfolds as a function of time. So that's what this red is showing. The red is showing how does the strength of the magnetic field basically relax down to the 0.3 nanotesla of the pristine interstellar medium.
Gotcha.
And so what you can see, so that
timeline here,
a rough timeline. And yellow is yellow just kind of shows what the area that the spacecraft covered in the year of 2022.
Yes. Okay.
And so the Voyagers are covering only a very small little area during this time. But in their futures, we have the whole future trajectory that we expect. But it answers this really big question of when does the magnetic field undrape? How far out do the Voyagers have to go? And if you zoom out, you can see that the answer is very different for Voyager 1 than it is for Voyager 2.
Ooh, quite. 400-ish versus maybe 900-ish.
Yeah, exactly. And maybe even if you're generous, 550 is close, you know. But it turns out that it will take a couple hundred years for the Voyager to reach there.
Yes.
And so this middle panel is there to illustrate what happens if we go into the nose direction. That's this upstream direction, that's the nose direction. And we even see a different trend there. We see that the magnetic field starts out like very large angle between the draped field and the undraped field. 60 degrees, 70 degrees, something up there off the chart. And then it undrapes really quickly over a short distance. So if Voyager had gone in that direction, it would have seen a more dramatic rotation in the magnetic field as the Voyager, as the spacecraft goes away from the helipause.
Indeed, yes.
And so, basically what this tells us is that you can actually see these effects for like a future mission. If there's a future follow-on mission to Voyager, you could actually choose how soon do you want to arrive at this undraped magnetic field. And we haven't fully run the simulation, but to first order, we think that the direction that you would want to go, if you were to point a spacecraft to encounter this undraped magnetic field as quickly as possible, it'd probably be towards the side, or what they call the flank of the heliosphere. So those are the highlights.
How fast you get there depends how fast you're going. So
yep.
All right,
Exactly.
you get there. Very cool. Very nice. Okay, that'll do. Very good. I really like this picture. I think it's a great plot.
Thank
Really
you.
do. All righty. Jamie, thank you so much for walking us through this very awesome APJ letter. Thank you.
Thank you for the invitation.
And you touched on it a little bit. You hit it a couple points, and so I'll just push on a couple of them.
Okay.
Where do we go with this over the next 2 to 5 years? Is there additional theoretical models that could be done that could improve, let's say, the B sub R? How about time-dependent models? Is there any possibility of getting additional data? Maybe there'll be a fortuitous event from the sun that'll shake it out there, and maybe we'll get something there. But just sort of what's our next steps over the next couple of years?
That's a really good question. So as far as this is concerned, definitely building out models to have time variations and understand kind of how does the disturbances that the sun causes when it makes these waves.
Oh yeah, yeah.
Medium, how does that change everything?
Yeah.
And for the spacecraft and the data that comes from the spacecraft, it's worth looking at that calibration in the interstellar medium and kind of comparing the approach that's being used now to what was used in the past, and making sure there's a distinct difference, because some of the assumptions that were made inside the heliosphere, they don't necessarily apply now. And so there might be just need to be a careful kind of revisiting of how exactly is it being calibrated, and does that make sense? And I think there's also kind of a hope of possibly, we'll see, I don't know, can't promise anything, but this could be solved in principle if the spacecraft were to do a maneuver where it carefully pointed. It wouldn't be able to go a wide angle, but it would basically do a yaw motion. And if it just did a motion like that, they'd have to be very careful, because they could lose kind of communication if they go way too far. But I think the ops team might know how far to do it. Then that would actually give them the ability to calibrate this R component kind of in an analogous way that they do the other two.
Yeah, I'm with you. Very cool.
Yep.
Yeah. And in fact, you would hopefully, or you had hinted that maybe there would be, let's just call it Voyager 3.
Yeah. Exactly. A Voyager 3 might have a magnetometer oriented in such a way that that it can basically measure these really weak fields, but also in a way that they can kind of calibrate, subtract out the spacecraft magnetic fields differently. And so that's another area. And then the other really exciting topic is that big change, that abrupt change in the magnetic field and plasma and stuff. And trying to understand what that means. Maybe that has clues about what's happening out there too. And so
I smell shock somewhere there.
Uh-huh.
Very cool. Good. Well, I really look forward to seeing this topic on the local interstellar medium advance over the next couple of years. It'll be very exciting to see it finally flatten out. Be great. Awesome.
That will.
All righty. Jamie, thank you so much again for walking us through the very awesome article. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.